Okay, so good afternoon, good day. So today you will learn about the multi-stage gas compressor. So previously we have discussed about the single stage compressor and its calculation and its examples. So today we will discuss the reason why we need to do multi-staging. So first is that multi-staging saves compressor power input. So the single stage compressor consumes more power than a multi-stage. So limit gas discharge temperature. So if the temperature due to compression is very high, so the oil will vaporize. So to prevent that from happening, that is why we need to do multi-staging. So third reason is that we need to limit the pressure differential on the cylinder, because if the pressure in the cylinder is too great due to single stage compression, when the pressure is too high, the oil cannot lubricate properly into the cylinder wall, thus causes damage to your compressor. So again, prevent vaporization of oil. So the most basic example of a multi-stage compressor is a two-stage compressor. So we will draw a schematic of a two-stage compressor. So we have two compressors here. Compressor 1 is a low pressure compressor and compressor 2 is a high pressure compressor. Okay, so the pressure inside the intercooler, so this is the intercooler, is known as PX, or sometimes it is known as the pressure intercool, or PI. So when we are going to draw the diagram in the pressure volume axis, it will look like this. So sometimes it's called PX because in a three-stage compression you have two interstage pressure, which is PX and PY. Now in a two-stage compression you only need to use PX or sometimes PI. So P1 and P8 have the same pressure, P4 and P5 have the same pressure, and P2 and P3 and P7 and P6 both have the same pressure. Okay, this is what it looks like under the TS diagram. So this is isentropic. Assuming this is an isentropic work, so this is where the intercooling happen. So T3 is also known as TX. This is our temperature 4. So in order to show that there is savings in energy, so in a single stage compression, from here we will go directly to the pressure final, which is P4. So the difference between the single stage and the double stage, this shaded part is the savings. So this is the energy we could save. Whereas here in the TS diagram, supposedly in a single compressor, it extends until this pressure high. So the shaded area shown in this TS diagram is also known as the savings in the energy. As you know that compression requires a very high energy level, so we need to trim it down as much as possible. So that is where staging comes in. Okay, so this first compressor here is where the LPC occurs, and also this is where the HPC occurs. So also here is the LPC, here is the HPC. So meaning compression from inlet 1 to 2, 1 to 2, 1 to 2. Then there is intercooling from 2 to 3. 2 to 3 is intercooling through the interstage pressure of the pressure intercooler So then it is then compressed back again to TX2 or T3 to T4 to the final temperature and pressure. So in order to calculate the total compressor work, we know that we have two compressors. So work compressor total is work low pressure compressor plus work high pressure compressor. So if we will going to expand it using isotropic, you could use N as the actual value for K, for a certain gas, because isotropic doesn't includes friction, but the actual value of N considering those irreversibilities is N. So basically based on our TS diagram, we use isentropic, so we will just use K. Anyway, if there is a actual value of K which is N, then we will just substitute it in the equation. But we all know that P3 is equals to P2 because they lie on the same graph, in the graph. So meaning we could replace this by P2. So if we will be going to combine these two equations, it will have this look. Since we also know that T1 is approximately equal to T3 because that is why we intercool, we need to bring back the exit temperature from low pressure compressor, the inlet temperature of the second compressor, the high pressure compressor should have a temperature that is equal to the temperature of the low pressure compressor at the inlet. So this is the total compressor work. Okay, remember that the reason why we intercool is that we need to bring back the supposedly from the low pressure compressor, it is compressed from point 1 to point 2. So in point 2, it has a rise in temperature. So we need to use the cooler or intercooler in which it is a heat exchanger that absorbs heat at a pressure px, so to bring it down back to the temperature of T1. So the exit temperature of the intercooler is approximately equal to T1, so therefore T1 is equals to T3 before T3 is compressed back again in the high pressure compressor. So that is the main idea. So in order to have the most optimized computation for power in the compressor, it should be that the work low pressure compressor is equal to the work of the high pressure compressor. And the same if for 3 stage, for 4 stage, it should be that the work of the first compressor is equal to the work of every other compressor. So we could then say that the total compressor work is simply equal to the number of stages times work of the low pressure compressor. So this is the general formula of the work compressor total, no? Because we will only equate all the succeeding compressors as to equal to the value of the low pressure compressor. So it is determined by the number of stages times the work low pressure compressor. So we will derive it, no? So how do we derive the interstage pressure? So it comes from this equation, that so remember that T3 and T1 had the same value. What are the only difference is the P2 over P1 and the P4 over P2. So all of the values will cancel out. What will remain is the pressure ratios. So when you do the algebra, so we will find the root. So the pressure at the second is sometimes called as Px or Pi. So this will now become the pressure interstage or intercool. So now that we know that the work compressor total is simply the number of stages times the work of the low pressure compressor. Where is the low pressure compressor? Here. The work of this compressor. So we know that we have solved the Px, no? So the Px is the pressure interstage. So therefore, revising the work compressor total formula, it should be the number of stages times what is our work? So K over 1 minus K times MRT1, which is the temperature at point 1, times Px because the exit pressure of the from point 1 to point 2 is Px. That is why Px over P1, K minus 1 over K minus 1. So when you are given a value of n, then just substitute K with n. So that is why we get that the formula for compressor work of 2 stages is 2 times this formula, or sometimes in terms of n. So it only originates from this, meaning the target is to make all other compressor work equal to low pressure compressor. So that is why I just multiply to the number of stages. Now to solve for the rejected heat, because there is a QR here, so we could solve for Tx. So Tx is what? Tx is T1 times Px over P1 to the K minus 1 over K. So now that we have Tx, we can now compute for the QR. QR is MCP Tx minus T1. So the 3 or more stage compression basically works on the same principle. So we will just make a 3 stage as an example. For example, we have a 3 stage compressor. So this is our low pressure compressor. This is our HPC1. High pressure compressor 2. So our final pressure is P6, our initial pressure is P1. So the reason why it is called sometimes in the two stages, sometimes this is called as PX, sorry. Because if there is another intercooler, it is termed as PY, and the third intercooler is termed as PZ. So that is why sometimes it is called PX, PY, no? So when we draw the PV diagram, so this is our pressure initial, this is our pressure final, so this is our PX and this is our PY. So this is where the intercooler happens, this pressure. So this is point 1, 2, 3, 4, 5, and 6. So see, pressure P6 is pressure final. So basically, with the same principle that the work LPC is equals to work HPC1 is equals to work HPC2. So when you are going to expand this through the compressor work formulas and cancel out the remaining, it will be like this. Okay, so based on the derivation, we could have a generalization that the Px in a multi-staging is equal to the root of the number of stages times the pressure initial S minus 1 times the pressure final. So this is now our, because it's the same thing, so even if it is 3 stage, 4 stage, 5 stage, it follows the same pattern, the same derivation. So even if it is 3 or more stage, the same Px is what we need, no? Because we need the work of the low pressure compressor at only need Px and P1. So again, even if it is 3 stage or more, the same pattern for the formula of the total compressor work. It is number of stages times work of the low pressure compressor. That is why we solved Px previously. So expanding this term using isentropic, so we need Px here because we used to find the work LPC. Okay, so if we are given with a value of n, we just use n, polytropic compressor work. So now again, if there is a rejected heat in the two-stage two-stage compression, there is also a rejected heat in the multi-stage or 3 or more stage compression. So the QR is simply equal to the number of intercooler, not the number of stages, but the number of intercooler times mass flow Cp Tx minus T1, because it's just the QR of the first intercooler multiplied by the number of intercooler.